Hello everyone, welcome to the biggest ideas in the universe. I'm your host Sean Carroll, and today we're doing a Q&A video for idea number 20, which was entropy and information. Unsurprisingly, to no one's astonishment, this topic generates lots of questions, lots of good questions. I know that, I've talked about this stuff for a very long time, and the questions are good because it's a very rich area, very important area, and it can be a little bit confusing. It's both conceptually confusing and also the vocabulary borrows words that have slightly different meanings than their technical terminology would imply. So you need to think about it a little bit. It's all figure-outable, and also, of course, I should mention, not all the questions here have been answered, right? I mean, we are actually trying to improve our understanding in some of these areas, so there are research-level questions that we run against. But anyway, all this is to say, let's not mess around too much. Let's just dive right in. Except, I do want to mention one more thing. I mentioned it already in the video, but I want to do one more plug for my book, From Eternity to Here, The Quest for the Ultimate Theory of Time, because this book really dives into a lot of the questions that were being asked in the Q&A and elsewhere. I talk in this book at the end about cosmology and the Big Bang and multiverses and inflation, but most of the book is devoted to the topic of entropy and its relationship to the arrow of time, why there is an arrow of time, what it has to do with entropy. Okay, so buy the book, that'll answer a lot of questions. Let's just dive in. And the first question I want to talk about is exactly this relationship between entropy and the arrow of time. The fact that the past is different from the future, versus time itself, we might say. So here's what happens, and I'm not exactly sure how to stop it from happening. I talk a lot about entropy and the fact that entropy increases over time in closed systems like the universe. I make the claim that asymmetry between past and future is what drives all of the asymmetries between past and future that we notice in our everyday lives, and therefore gives us the arrow of time. And so people seem to feel that they want to therefore identify entropy with time, or the second law of thermodynamics with the change of things over time, something like that. So I want to distinguish between these two things. They're extremely different things, even though they're related to each other and they kind of sound the same. There is time, which is a coordinate on spacetime, right? Or something that your clocks read, right? Time is a way to locate yourself. We did a whole Biggest Ideas video on time and what time is. Then there is the arrow of time, which is a very, very specific feature of time in our universe. So no one is saying that entropy is responsible for time, or that the growth of entropy is responsible for time, or anything like that. If you're ever tempted to think that something like that is supposed to be true, just think of space. Think of the analogy with space. In Newtonian mechanics, just like in relativity, there's a similarity between space and time. These are ways of finding yourself in the universe. They are measures that help you locate yourself with respect to other stuff. If you want to find yourself, if you want to tell somebody where to meet you, you tell them where you're going to be in space and when you're going to be there in time. None of that has anything to do with entropy or the arrow. There is no arrow of space out there in the universe, but there is still space, right? The existence of space does not require an arrow of space. As we mentioned, there is an arrow of space here in this room. If I take the pen and I drop it, it will always go down. We all know that's because we're in the vicinity of the Earth, and entropy is like that. So the existence of the Earth and its gravitational field gives rise to an arrow of space, but space would be fine even if the Earth were not here. Likewise, the increase of entropy over time gives rise to an arrow to time, but time would be fine if entropy were not there. There's a related question, what about entropy decreasing subsystems in the universe? So if I take my favorite subsystems, that was pretty bad, subsystems, my favorite example is putting a bottle of champagne in the refrigerator. Its entropy goes down, okay? Does that mean that it gets younger, that its arrow of time reverses? Well, no, that is not actually true. And part of me wants to just give a glib answer here. I mean, the question is, if you can locally decrease entropy in some region, does the arrow of time reverse? The answer is no. But, okay, so why is that true? And part of me wants to just say, well, Look, the arrow of time is a more global phenomenon, okay? If you're lowering the entropy in that bottle of champagne, it's because you're increasing the entropy somewhere else. By itself, it wouldn't happen. It's not the spontaneous flow of a system from high entropy to low entropy, so it doesn't really count as the arrow of time. And I think that's true as far as it goes, but part of me also wants to admit that this is a complicated question, and I don't personally have a fully worked out answer to this question. I think it depends on the circumstances. I think that if you had a large enough and sufficiently complex system that somehow its entropy was set to decrease in the right way, you could get a reversed arrow of time. But even that, it's not exactly the same as putting in a refrigerator, okay? I mean, if you had a box of gas with all of the molecules bouncing around, I could imagine, just in thought experiment land, freezing the box, delicately arranging the momenta of every single molecule so that they're in a specific, incredibly finely tuned configuration that will decrease in entropy over time. And then maybe you get a reversed arrow of time. That's the actual time reversal of the ordinary situation. That's not what you have in a refrigerator. In a refrigerator, there's no prearrangement of the atoms or the molecules in the champagne bottle. They're just bumping into the walls of the champagne bottle, and it's in a lower temperature environment. So it gradually decreases to a lower entropy state. There is a difference between those two things. You are decreasing in entropy because of fine-tuning of your initial conditions, and decreasing in entropy because you're in contact with some lower temperature heat bath. I am sure that difference makes a difference for understanding the arrow of time, but to tell you the truth, I couldn't completely work it out. So this is one of the examples that I wanted to give of something that is, worth thinking about. It might be worked out in some paper by Reichenbach or something. In the 50s, I really don't know, but it's a good question, but ultimately, just because I unshuffle a deck of cards does not mean its arrow time is decreased. Okay, it's not a closed system by itself. Good, that's one question. And another question is, I gave you, I think, 4 different definitions of entropy, and I didn't give you the most basic one. So let me give you another definition of entropy, what we might call a thermodynamic entropy. And of course, in some sense, the other entropies we talked about are all thermodynamic in some sense. But remember, I did say that the concept of entropy was invented before Boltzmann came along to give us the Boltzmann entropy, or before Gibbs and Boltzmann and others gave us their formulas for entropy. So clearly we had some definition of entropy even without all this machinery of statistical mechanics and coarse graining and so forth. And so Clausius is the guy who generally gets credit for this, Rudolf Clausius. And this becomes very complicated and very ugly, because this is in a world where we're imagining that gases or fluids or whatever have things called temperatures and pressures and entropies, and that's it. Okay, they're not derived from some underlying microscopic description. They're phenomenological properties of the thing itself. So you don't need to pick a coarse graining or anything like that. You don't need to know what the molecules are made of. You can still talk about all this stuff. But it's hard because, there's a lot of different things that can happen in that messy phenomenological world. You have to be very, very careful. Are you doing a process at constant temperature, at constant pressure, at constant volume? Remember, any one of you in the background, in the audience who have taken thermodynamics courses, you remember all the difficulties here. By the way, all those difficulties that you had, if you did take a thermodynamics course, in keeping straight all those partial derivatives with respect to different things, keeping other things constant, it all makes sense if you first learn differential geometry. So all of those different choices of variables to use on state space, it all makes perfect sense if you just couch it in the language of the same kind of differential geometry we use in general relativity. Okay, manifolds and vector fields and all that stuff. Now, it never happens that you learn differential geometry before you learn thermodynamics, so there's very few courses taught in that language, but I just want to let you know the understanding is actually out there. Anyway, all that is to say, here's the definition of entropy. The change in entropy is equal to the change in heat of a system divided by the temperature. So we're imagining that we have a system, and it's embedded in a heat bath, and the bath is at temperature T. And so the system is like the champagne bottle, right? It could have a different temperature overall, and so it exchanges heat with its surroundings. The bath has a constant temperature, and that change in heat with the surroundings is going to level off to zero, right? It's going to change heat. Either it's going to take in heat if it's colder than the surroundings, or it's going to expel heat if it's warmer. And so this could be positive or negative because it's not a closed system. But eventually it comes to the same temperature and the exchange of heat stops. So there's some finite quantity you can get by integrating this change in heat, okay? So this is nice, and this is what we call a state variable of the thermodynamic system. Now there's all of these caveats here. I'm not going to get into all of them. One of the reasons why I didn't talk about this is that a lot of the discussion, not all of it, but a lot of it in this language only makes sense if we think about equilibrium systems. So we think about systems that we've let settle down, or ones that we have almost let settle down and we move them very, very gradually. Okay, we don't put a huge shock to the system and let things mix up and go crazy. That's a harder problem. That's non-equilibrium statistical mechanics. And so you get grown-up physicists who learned this when they were undergraduates, and they were taught that the very idea of entropy only applies to equilibrium systems. Why? Because they were only told the definition of it for equilibrium systems. But clearly, the definitions we gave from Boltzmann or Gibbs or whoever apply all the time. They require that you have some kind of coarse graining, so it's a little bit more subtle. So there's a trade-off involved in the usefulness of these notions. But you can show, I mean, this is what Boltzmann and Maxwell and other people did, that this definition of entropy from Clausius can be recovered in statistical mechanics using the different definitions we gave. So this is yet a fifth definition of entropy that you might be interested in. Speaking of which, let's talk a little bit more about coarse graining. By coarse graining, I mean, remember we talked about the system that has a phase space, and you have microstates, which is the exact configuration of positions and momenta in the phase space. But then you say, look, macroscopically, I can't tell the difference between some of these arrangements, so I'm going to put them in an equivalence class that I call a macrostate. And the volume of that macrostate, take its logarithm, that's Boltzmann's definition of entropy. And so I'm sure that I said this in the original video, but I forget exactly how much I said, so I'll say it again, and hopefully it will help clear up some of the questions. People get bugged by this because they say, well, you know, that coarse graining seems to be subjective. It seems like I made it up. But somehow you're telling me that it explains why coffee cups always cool down, right? You know, like that seems like I'm explaining some empirical phenomenon of the universe, which is absolutely universal and predictable, on the basis of choices that I subjectively personally make. That doesn't sound like something that should be in the laws of physics. So I'm sympathetic to this critique. Remember when we talked about quantum mechanics and the collapse of the wave function, I was and remain horrified by the idea that something like the measurement postulate in Copenhagen interpretation of quantum mechanics, you measure a principle of a system, a property of a system, and the wave function suddenly and unpredictably changes. That doesn't sound to me like something that should be in the laws of fundamental physics. If you have no choice, then okay, but you better at least make precise what you mean by measure, okay? So likewise, it's a perfectly legitimate thing to say you better make precise what you mean by this coarse graining. So I'm not going to say a lot about this, but let me just reiterate that even though we use a language like what I can measure about the system, what I can macroscopically observe, what I actually in fact can measure is not arbitrary, okay? The laws of physics constrain what I can measure about a system. So, people were asking about, like, what if I have a bunch of molecules, but some of them are painted green and some of them are painted yellow, and I'm colorblind, so I don't know. So there is something called the entropy of mixing that does, in fact, keep track of whether or not you have segregated systems by some property that doesn't affect their motions in any way, right? Like two different kinds of molecules that have the same weights or velocities or momenta or something like that. But you can't really use it to do work. Like, you can't, it doesn't carry energy with it, but it does increase over time. So all this is figure outable. What I want to get at more is the way that we actually do coarse grain in real physics is driven by real physics, is not driven by our subjective choices. When we look at a system, we're looking at it using photons, okay? And those photons come from the boundary, and they have, certain wavelengths, and more importantly, they're sensitive to certain things. In other words, the laws of physics and what they enable us to straightforwardly observe determine to a very large extent how we coarse grain the universe into macro states. And this is particularly important because some people have suggested, do we automatically have a past hypothesis? What I mean by this is the past hypothesis is the idea that the early universe starts with low entropy. And given that there are many more ways to be high entropy than low entropy, it will naturally grow. Everything makes sense. Congratulations, it all fits. But some people have said, look, if your definition of entropy depends on the coarse graining, you can give me any trajectory of the system through state space. Okay, start with some actual microstate and let it evolve through state space. And after the fact, I can coarse grain it so that entropy looks like it's going up. So in other words, if here's all of phase space, gamma, okay, phase space, and here I have some system that starts here and goes there, right? There you go. And I'm going to say, let me change colors here. Let's say once I know how it actually evolves, I'm now going to coarse grain like this. So here's a macro state, there's a macro state, there's a macro state, and I'm going to say, entropy goes up. But I notice I could equally well, so the argument goes, coarse grain this way. There's a macro state, there's a macro state, there's a macro state. And now along the same direction entropy was going up, now it's going down. So there's the idea that I can just, after the fact, make entropy go up or down just by choosing my coarse graining. So this is why I feel the need to insist you don't get to choose arbitrary coarse grainings. You can fiddle around the edges a little bit, okay? But there is something real, something objective, something that is fixed by the laws of physics about how we actually choose to coarse grain. When we say that we have some collection of molecules in a room, like you open a bottle of perfume and the scent goes out. This is an example that Boltzmann, I think, actually looked at, right? And you say, well, look, the entropy is increasing as the gas fills the room. What are you doing? You're coarse graining by the density of gas in physical space. And as we talked about a long time ago in the video about, space, there's a reason why we coarse grain things in space, right? According to location in space. We could coarse grain them in momentum space or in some complicated non-local combination of things, but then the emergent laws of physics would look like a mess. You wouldn't get any pretty straightforward, understandable behavior. There's a reason why we coarse grain in the way we do. And it's with respect to that very natural coarse graining that entropy started low in the past and is increasing toward the future. Another question that is related to this was, look, if Gibbs says the entropy is related to our knowledge, and our knowledge of the universe doesn't change over time, so that the Gibbs entropy in a closed system just stays constant, then how does entropy go up? The answer is it's the Boltzmann entropy that goes up. It's not the Gibbs entropy that goes up if you don't look at the system. But the Boltzmann entropy does. The Boltzmann entropy requires this coarse graining, but nature and the laws of physics give us a coarse graining that makes perfect sense, okay? It's not nearly as arbitrary as you might think. There is something, with respect to that, so let me just actually mention, again, I forget what I mentioned when I made the video, but let me mention one little wrinkle on that question of the Gibbs entropy remaining constant in a closed system. So if you have a closed system, and the Gibbs entropy, so remember the Gibbs entropy, at least what I was calling the Gibbs entropy, don't take too seriously the connection between labels and actual historical events. The history of this is very, very messy and fascinating. But it is minus the integral of some probability distribution times the log of that probability distribution over d gamma, if you want to call it. If this is gamma, the whole phase space, there's a tiny element of gamma, and p is the probability associated with that particular point in phase space gamma. Okay, so this tells you how much you know about the system. It's some probability distribution, p of gamma. And it's going to evolve in time. And if you know the microscopic laws of physics, this quantity, the Gibbs entropy, remains constant. ds Gibbs for a closed system, dt equals 0. And that's not the second law of thermodynamics. Nothing's going up, right? Okay. So this is a little tiny bit of a puzzle. The real resolution of the puzzle is easy. It's the Boltzmann entropy that goes up. Or if you have a closed system, but it is if you have a not closed system, if you have a system that is in contact with a heat bath, then there's a version of the second law that uses the Gibbs entropy. But what about this question? So what if I have a closed system, a system that is usually closed, but there's a window, and occasionally I can open the window and look at the system, right? Then you might think, well, when I look at it, if I look at it in a way that doesn't disturb it, so it's not quantum mechanical, it's classical, I just look at it, see where the gas is, roughly speaking, and I close the window again. Didn't I learn something about the configuration of the system? And therefore, you can make a more sharper sounding paradox. You can say, doesn't it seem like the Gibbs entropy only ever goes down? Okay, and isn't that bad? Isn't that the opposite of the arrow of time, the entropy only going down? You have to keep your wits about you because there's many different definitions of entropy. So that's a simple way out of that dilemma, but you might want to know what's really going on here. So I actually wrote a paper with some colleagues of mine, Tony Bartolotta, Jason Pollock, Stefan Leichenauer, where we invented what we called the Bayesian second law of thermodynamics. So we talked about Bayes' theorem in the probability video. Bayes' theorem is a way to update your probability distributions, and usually we think of that as a set of credences on propositions or theories or something, but you can think of it as the probability distribution on the configuration space or the phase space of a set of molecules. Sure, why not? So you can use Bayes' theorem to say, if I have some probability distribution on phase space, and then I look at it, I make a measurement, okay, then I can update my probability distribution. And indeed, you can show that the Gibbs entropy should go down, just like that makes sense. Your knowledge increases, the entropy goes down. But there are other things that go up, is the point. What is happening is, from the information point of view, there's an exchange of information, right? You didn't have that much information. You have more information now. But what we were able to show, it's a very complicated thing, I'm not going to go into details, but there's something called the cross entropy that relates the distribution of molecules before and after you made the measurement, and the cross entropy always goes up over time. So there's a sense in which, even though you're learning more and more about the system, there is something that irretrievably loses information, even when you're learning about it. So there's always a version of the second law that you can't escape, no matter how hard you try. Okay, let's change gears a little bit. Let's expand our horizons. I wanted to start with some of the basic thermodynamic entropy stuff, but then a lot of the questions wants to stretch beyond the parts of the story that we understand very, very well into the parts involving gravity or cosmology or field theory or something like that. So why not? It's the Q&A. We can do that. So let me talk a little bit about entropy and gravity. And an obvious question is, do we understand entropy in the context where gravity is important? I gave examples where you have a box of gas and gravity is not important, by which we mean the mutual gravitational force between the molecules. I mean, it can be in a gravitational field sitting on a table. That's a different thing, but the mutual gravity is not important. And there we know exactly what the formulas are for entropy. That's the conditions. Those are the situations that all the people in the 1800s were actually caring about. Whereas in the early universe, when we said, yes, it looks like a black body, but it's actually low entropy compared to what it would be, the reasoning was that because then gravity was really, really important. So you're very allowed to ask, so what's the formula? So how do we actually calculate the entropy of a box of gas when the mutual gravity is important? So there are things we know and things we don't. So we do understand it perfectly. We understand it for Newtonian gravity. I'll explain what I mean by that in a second. So what I mean is, you have a box of gas. It might be a big box, right? Megaparsecs across if you want. So here's some gas. And so the gas, we use the word gas in a very broad sense. The gas might be stars or galaxies for that matter. And what is gravity in this case? If you are in the regime where gravity is just Newtonian, so there's a force which is Newton's constant, mass of 1, mass of 2 over the distance squared between any two objects. Well, it's exactly the same. There's no difference whatsoever. You can coarse grain by like volume or something like that. But the point is that what the gravitational force does is change how there's an interplay between space, the space, the locations in space, and momentum space. So what happens is things want to come together under the force of gravity. So let me actually erase. Well, let's just keep the picture there, but draw another picture. So let's imagine we start with a bunch of particles that are relatively spread out and watch them evolve under Newtonian gravity. Well, they will seem to collapse, it's true, but they will also speed up. Okay, so even though the spatial configuration is shrinking, that does not necessarily by itself correspond to decreasing entropy. In a box of gas, it would, because you have the box of gas, you put all the gas in the corner, you just let it go, the box of gas with no gravity in it, well, then it just expands through the box, but the individual motions of the molecules retain their average velocity. The average velocity doesn't change, only the spatial extent changes, and therefore the entropy goes up when you fill the bigger volume. Here, you're filling a smaller spatial volume, but the reason why is because you're being attracted to each other under the force of gravity. So your velocity increases. So even though the spatial extent that you would see just by looking at it seems to go up, if you're coarse graining by putting in an equivalence class where you don't know the velocities, there is more phase space available here because the velocities have secretly increased. And then what can happen further is there's no end to this. There's no limit at which the ball has a certain size and shape, the mutually attractive collection of particles reaches some size where entropy is maximized. It never happens. What happens is most of the particles just come closer and closer together, and a few of them fly off to infinity, right? They can just escape. And this literally happens when you make a galaxy. Like, galaxies are not exactly in thermal equilibrium for exactly this reason. They can be pretty close, but they can always shrink. Clusters of stars or anything can always get smaller just by spitting out other things with hugely high velocities. Okay, so the Newtonian story is pretty straightforward. It's a little bit different than the non-gravitational story, but it's not hard to understand. Now, one of the reasons why there's no ending here is because one of the reasons why I said Newtonian gravity is there's no black holes in this story, right? There are no black holes in Newtonian gravity. So there's no point at which everything just collapses to a black hole and then evaporates. But in general relativity, that would happen. Now, in general relativity, there's another thing that happens, which is that you have gravitational waves. There are degrees of freedom in general relativity, namely independent fluctuations of the metric field, of the gravitational field, that in Newtonian gravity you don't have. In Newtonian gravity, you can talk about the gravitational field. Laplace introduced it, the gravitational potential, but it doesn't propagate by itself. It doesn't have a life of its own. Once you tell me what the matter objects are doing, the masses and energies, you completely determine the gravitational field. In general relativity, that's not true. You can tell me exactly what the matter objects are doing, but you still haven't yet told me what the gravitational waves, the intrinsically gravitational degrees of freedom are doing. So for the gravitational waves, in some regime, you can treat them just like photons, right? Like if you could imagine just quantizing them and averaging over the number density in a region, then the gravitational waves are more or less just like photons. But that's not always the regime you care about, right? When you're near creating a black hole, things become more complicated. So in GR, you have, of course, you know what the entropy is for black holes. The entropy, the Bekenstein-Hawking entropy for a black hole, we talked about this in a Q&A video. By the way, some people are asking questions who haven't actually watched the other Q&A videos because we talked about some of these. So we talked about the black hole entropy quite a bit. So it's the area of the event horizon divided by 4 in units of the Planck length. So we can just write L Planck squared, okay? So once you've settled down to a black hole, then you know exactly what the entropy is. And you know in particular that the entropy of a big black hole is way bigger than the entropy of the mass it was made of. Okay. So we don't have a full story or set of equations for the entropy of a fluctuating gravitational field in general relativity, but we have a good enough set of approximations that are good in different circumstances. The other question that is asked then is, well, that black hole evaporates, right? Does the entropy go up when it evaporates? So I just told you a story where, in Newtonian gravity, the entropy is increased by things coming together mostly, and a few things get spit off to infinity. If I say that in general relativity, this story goes, now I get a black hole, right? Looks like a white hole here on the tablet, but there you go. This is a black hole, okay. Now that black hole is going to begin to radiate, right? That's what Hawking taught us. So the black hole eventually evaporate away. So which is it? Is it that with gravity, things want to clump together in a high entropy state, or with gravity, things want to evaporate in a high entropy state? Because this black hole eventually evaporates away entirely, and you're left with nothing but a gas of photons again. Isn't that where you started? Well, the answer is it's complicated. We know what the answer is. It's just a little bit complicated. It's not a simple, concentrated means high entropy or low entropy or vice versa. It's a little bit more subtle than that. So in this original picture over here, where we just had the gas, we were assuming there was some density of gas, and we didn't worry about what things were like outside, what the rest of the universe was. If the rest of the universe also has particles in it with the same kind of density, then they will clump together locally in the same way as this one did. They will form a galaxy. This is what actually happens in the early universe, right? You have this collection of particles. They come together under gravitational attraction. They form galaxies. Entropy is increasing during that process, okay? But then what happens next? And usually we stop telling you the story then, because that's the current universe right now, right? We formed some galaxies. There's empty space in between. We know what's going on. If we follow the story to the point where either we care about the stars that were spit out, or we actually form a black hole and we care about the photons that are spit out, now we have to wonder about what is happening with the expansion of the universe overall. So if somehow we were living in a non-expanding universe, then roughly speaking, you would get a constant churning of exactly this process. Things would come together. I'm imagining some very fake universe where you can make black holes, but the universe is not expanding. Okay, so maybe it's like the Einstein static universe or something. So what would happen is you come together, you make a black hole, it evaporates, but then all those photons have energy, and other black holes elsewhere are also emitting photons, and they would come together to make black holes again, and then they would evaporate, and there would be constant churning back and forth. But that doesn't sound right. Like, that doesn't sound like the final result. We're taught in thermodynamics that things eventually reach an equilibrium. What would happen is that the sizes of the black holes you would make and the sizes of the empty space around them would grow over time. Like if I have one black hole with a certain entropy, that's good. That has a lot of entropy per unit mass. But if I have 10 black holes of the same entropy, I can certainly increase their entropy by smushing them together to make one big black hole. Okay, it's entropically favored to make big black holes rather than small ones. So what happens is that the scale of lumpiness in the universe would just grow and grow and grow over time. So it's churning, but it's not sort of equilibrium churning. That you never reach an equilibrium in this sort of weird hybrid static space but creating black holes kind of universe. You grow structure and structure on ever larger scales. Now that doesn't happen in the real world, because in the real world space is expanding, right? And we think that space is going to expand forever. We think that there is dark energy that is pushing it apart. We don't know, but that's certainly a plausible possibility. And in that case, the other lumps of matter that were made by black holes elsewhere are just going to get further and further apart from each other. So now it is no longer necessary that all these photons emitted by black holes meet other photons and create other black holes. They can just expand apart from each other as the universe becomes more and more dilute. And so the question is the entropy of these photons that you get by the black holes evaporating, is that greater than the entropy of the black hole? Yes, it is. But it also takes up a hugely larger amount of space. So if there is enough space for that set of photons, and also gravitons and neutrinos and so forth, if there's enough space for that gas of particles into which the black hole radiated to just keep expanding and diluting without bumping into other matter, then that will be the endpoint. of the evolution of this system. So in fact, there is a theorem, the cosmic no-hair theorem, which was, I think Bob Wald from the University of Chicago first articulated this. If you have a vacuum energy, lambda greater than 0, either the universe recollapses. So if you have vacuum energy greater than 0, but the universe is closed, and so it expands, but the vacuum energy never takes over, the density of matter is always greater, then it can just recollapse, okay? Or space empties out. And that final state is called de Sitter space. Wilhelm de Sitter, famous general relativist, friend of Einstein's, they worked together, and he showed that the solution with nothing but vacuum energy is an eternally expanding space. So all the lumpiness that you might want to have evaporates away in the far, far future of the universe. You see why it's called the no-hair theorem. Very similarly, like the Earth or the sun or some object can have all sorts of interesting features, oceans, continents, and so forth. But once you make a black holes have no hair, all that's left is the mass, the charge, and the spin. Likewise, a universe can have all sorts of interesting features, galaxies and supernovae and so forth. But eventually, if you let it all expand away, you're left with a featureless de Sitter space. Okay? And in fact, you might say, I always wondered, one of my favorite papers that I've ever written was just a couple of years ago with Aidan Chatwin Davis, former Caltech graduate student. This statement that as the universe expands with positive cosmological constant, it approaches this universal future state, right? De Sitter space. Just like there was this relationship between black holes and thermodynamics that Stephen Hawking used to invent black hole radiation eventually, this also kind of sounds like equilibration, like the second law of thermodynamics, right? Like entropy increases and you eventually reach de Sitter space. And I think that a lot of people knew for a long time, know is a very strong statement in these sort of quantum cosmological realms, but a lot of people were willing to accept for a long time that there was a sense in which de Sitter space, an empty universe with nothing but a cosmological constant, was a maximum entropy state of the universe, given certain conditions. But what we actually showed, we proved a theorem, borrowing technology from Raphael Bousso and Netta Engelhardt and others. We were able to show that you could derive a version of the cosmic no-hair theorem from the second law of thermodynamics. So in other words, rather than what Bob Wald did, which is say, here is Albert Einstein's theory of general relativity. He gives me equations, Einstein's equations, and I show that I approach this empty de Sitter space, this bald universe with nothing in it. We did not actually assume Einstein's equations or any other field equations for the gravitational field. All we assumed is that entropy increases. And we secretly, of course, smuggled in the dynamics of gravity by saying we did assume this. There's this. This is the Bekenstein-Hawking formula for the entropy of a black hole. Hawking and Gary Gibbons later generalized this to de Sitter space. So there's also a horizon in de Sitter space, and it has an entropy that is, guess what? It's area divided by 4 in Planck units. So we assumed this equation, and that's where we derived the fact that there is a cosmic no-hair theorem. So we really made precise that under certain circumstances, the expansion and emptying out of the universe really not just goes along with, but is the second law of thermodynamics in action, which is very pretty. I always suspected that was true, and it was nice to be able to show it under certain circumstances. Okay, big shift of gears now. This isn't so much a question. There were questions here, but I'm not exactly sure how to phrase what I want to say as a question. So let me just write down topics. Life, information, and error correction. So once again, there's in this field, there's a whole bunch of lore. There's a whole bunch of things people think are true, and probably are true. They make sense, but that's a little bit different than having a rigorous quantitative theory of what's going on. So, like I just said, for entropy and the expansion of the universe, it was nice to have a theorem that actually related the two of them. Another thing that we say is, look, life can't exist in thermal equilibrium. That would be boring. Right? Thermal equilibrium, by definition, is whatever. If you listen to my recent podcasts with Stuart Bartlett or older ones, where we talk about the definition of life, being out of equilibrium is a crucially important aspect of the issue. So what does that mean? Why? Like, what are the precise exact ways in which the process that we call life relies on the fact that we're out of equilibrium and entropy is increasing? Okay? Well, one way is that life is kind of rickety, right? Like life is a complex system. It's like a car, right? It breaks down eventually. Like your body, your cells are dividing and your DNA is ripping apart and giving RNA information to make proteins and all this stuff. And there are errors made along the way. And, to be honest, like the idea of error correction is one that I'm increasingly impressed with as a fundamental feature of the cosmos. There's something called quantum error correction, which is very important for people doing quantum computing. There's also classical error correction. So the quantum error correction people were building on the classical theory of error correction. It's harder to correct quantum errors than classical errors, which is why you need an entirely different theory of it. But the very idea of error correction and its connection with entropy and the second law is crucially important. Like you would think, again, it's just like the existence of complexity itself, right? You ask the question, well, how could there possibly be spontaneously coming into existent complex systems if all that ever happens is entropy? But then you ask the question a little bit more sophisticated way, and you realize the only reason why complex systems can ever come into existence is because entropy is increasing. So similarly, analogously, you can say, well, why in the world should systems be able to correct errors in a world where entropy is increasing? Shouldn't errors just become more and more frequent? And then you analyze it and you realize the only reason why systems can correct errors is because entropy is increasing, because they live in if entropy is increasing, one of the prerequisites for that is that entropy is not yet maximal, right? If it were maximal, then it couldn't be increasing. So when you say entropy is increasing, you're smuggling in the statement that the entropy is not maximum yet. And that lets you correct errors. I'm not going to go through the whole theory of this because I don't know what the whole theory of this is, but let me give you the basic idea. Maybe someone in the audience can figure out what the whole theory is. So by error correction, we mean, let's say you have, some signal or some information. Maybe it's literally a DNA molecule. Maybe it's a protein that is going from one place to another. Maybe it is a set of nerve impulses in your brain that is going from one synapse to another. And let's symbolically say you have symbol ABC, or word ABC made out of 3 symbols, okay? And you want to send it down some channel, just like Claude Shannon talked about sending information down channels, and there's an error rate. Things can get mixed up. And so by mistake, it goes through the channel and it comes out AXC, where X is some other letter. So there's an error, B changed into some other symbol. How do you know, right? Like it looks, because I wrote it ABC, and that looks very different than AXC, but these could be anything. So in principle, you don't know what it changed to. So the principle of classical error correction, and again, I'm not doing justice to an entirely huge complex field here, but roughly speaking, you build in redundancy to the system, right? You say, okay, instead of just sending the signal ABC, I'm going to send A, B, 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 C, C, C. And the principle that I'm taking advantage of here is that errors are rare. Like if errors happen all the time, then you're doomed, okay? Well, you're clearly going to be doomed. If you have such a noisy channel that it's impossible to send information, then you're doomed. So what we're imagining here is you're pretty good at sending information, but occasionally there will be errors and you're not sure a priori when they've happened. So, but if you send this kind of redundant thing, then a rare error means that there's a chance for every one of these letters that it will randomly be changed. So it might change into A, B, B, X, C, 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 right? The chances that all 3 of the B's are going to flip into X is that much smaller than the small chance that even one of them would. So then you can clearly see how to correct this error. If you know that you're supposed to be sent a signal where there's redundancy, where there's three letters of the same type in a row, and you get something like this where there are not three letters in the same type in a row, then you say, well, majority rules. I'm going to correct that error to make it B, B, B. If I were unlucky enough to have two of them flip, then, so much worse for me. But if I make bigger and bigger words out of these letters, then I can always guarantee that my error rate will be small unless it's 100%, right? I can always make it, or, there's some cutoff anyway. So the point is, to do this kind of error correction, we need to increase the entropy of the universe. This is the Landauer principle, right? We need to erase that error that we made and correct it into something else. So we need to have the ability to undo that error by creating entropy elsewhere in the universe. If we were at maximum entropy, we couldn't do that. We wouldn't have the ability to. So our ability to correct errors like this, which is important in our cells, dividing, like being damaged, DNA suffering along the way, it's all possible only because we can do things very far from equilibrium. In other words, because there is an arrow of time. Again, not all the theory has been worked out. There's plenty of room for improvement here, but this is the basic idea. I think it's pretty powerful as well as pretty. Okay, now we're going to switch for the final set of topics. I want to switch to things that nobody understands. These were the last couple things we talked about were things that we have a pretty good idea what's going on, but details are murky. Now we're going to go beyond what anyone understands. Okay, but we're going to speculate about the ends of space and time. So let's talk about the number of degrees of freedom in space-time itself. And obviously, we don't know that. And I'll tell you the connection to entropy in just a second. Because this would require some knowledge of either the theory of everything or at least quantum gravity or something like that. Now, we do know, so what do we mean by this? Okay, we talked about, long ago, when we were talking about quantum field theory, we talked about quantum fields in a region. So this is space, this is some region A, okay? And, well, how many degrees of freedom are there in a region? In quantum field theory, the answer is infinity, right? And that's because there are waves of this wavelength, and waves of this wavelength, and waves of this wavelength, and waves of that wavelength, and an infinite number of waves, an infinite number of modes that you can fit inside there, okay? And then you say, well, okay, but let me imagine I put a cutoff. I don't let you have waves above a certain energy per mode, but above a certain energy per particle, I should say. But equivalently, I don't let you have waves below a certain wavelength, the Planck length or whatever, okay? Then you say, well, okay, now I have a finite number of degrees of freedom. But you're wrong. You cheated. You do not have a finite number of degrees of freedom because each one of these little waves I drew has a wavelength, but it also has an amplitude. Remember, if you go back to our quantum field theory discussion, every one of these modes acts like a simple harmonic oscillator in the free field approximation anyway. So for any one wavelength, the amplitude of the vibrations can be arbitrarily big. It corresponds to not the energy per particle, but how many particles are in that particular mode. So if they're fermions, then they might only have a finite number, but there are bosons in the universe, and bosons you could pack an arbitrarily large amount of energy into any single region of space in quantum field theory. So even with an ultraviolet cutoff, even with the shortest wavelength, and even with what you might call an infrared cutoff, you have the size of the region, there is still an infinite number of modes that you could fit in quantum field theory. And I keep saying in quantum field theory because quantum field theory is not necessarily the right answer. So now let's imagine turning on gravity, right? When we say quantum field theory, what we really mean is quantum field theory in some space-time background, either truly in Minkowski space, where you just turned off gravity, or you can do what's called quantum field theory in curved space-time. You can have a gently curved space-time and still do quantum field theory there. That's where we can make these statements about quantum field theory. But you don't let gravity be arbitrarily strong. However, if I just say, look, I can put an infinite number of modes in this region of space by putting more and more energy into that region of space, then clearly that's in conflict with the idea that gravity is not too strong, right? If I have an arbitrary amount of energy in a region, gravity is going to start becoming really, really strong. So Bekenstein, the same guy who came up with the idea that black holes should radiate and have entropy, pointed out that there is a bound. I mean, what we call the Bekenstein bound refers to different things in different people's hands, but the way that I like to think about it is there are not an infinite number of things you can do in this region if you actually have gravity turned on and let it exist, because most of the infinite number of things you thought you could do would be more energy than you can put in that region before you make a black hole. So there's a finite number of modes that you can turn on and excite without making a black hole, or you could make a black hole, but black holes also have a finite entropy. Here's the formula for the entropy, right? Remember, the entropy is the logarithm of the number of microstates that look like that. So this finite entropy corresponds to a finite number of microstates of the black hole. And so you include both quantum field theory states, where gravity is not yet strong, and you include the black hole states, but there's still a finite number, okay? So this is the idea, and this is not something that is well understood, okay? This is not something, I told you that this is not something that we all agree on, but I am on the side of people who think that in a region of space, there's a finite number of things that can happen, and what that means is that quantum mechanically, the dimensionality of the Hilbert space corresponding to that region A is finite. In fact, I think I know what it is. If you have the area, I shouldn't have called this region A, but so you have the boundary of A, which we call B, boundary of A is B, then the entropy associated with a black hole of that size, the entropy SA, would be the area associated with the boundary B divided by 4 L Planck squared. And if you have a maximum entropy state in quantum mechanics, the entropy is, let's get it right, the dimensionality of Hilbert space is e to the entropy. So I claim that there's factors of 2 and things like that we're not going to pay close attention to here, but the dimensionality of the Hilbert space of things that can happen in region A is e to the power of the area of the boundary in Planck units. So a finite number, but a really big number, because the Planck scale is small and macroscopic areas are large, okay? Now, I think this is a consistent story to tell, and it's consistent, for example, with the story we told about the cosmic no-hair theorem. I mean, there's a finite number of degrees of freedom in our universe because we have a horizon around our universe. There's a fixed size that we can get to, and therefore only a finite number of things that can happen. And this is also very compatible with ideas that I love from how gravity could emerge, how space-time itself could emerge from quantum mechanics, right? This is the idea that Charles Tao and Spiros Michalakis and other people have been thinking about, how you can just start with fundamental finite number of gravitational degrees of freedom and emerge space-time in some way. However, this is utterly incompatible with quantum field theory, right? In quantum field theory, again, in a fixed background, you have an infinite number of degrees of freedom in every region of space. And this a little song and dance I just told you seems to imply there's only a finite number. And you might say, well, so there's 2 things here. One is this glib statement I made, that gravity does not seem to be described by a quantum field theory. This is the evidence for that. This is the best evidence for that. I mean, there's more evidence from holography and black hole information loss and things like that, but this is a simple, straightforward, in-your-face piece of evidence that quantum field theory is not the right framework in which to do gravity. That's an incredibly dramatic statement to make, okay? It's not at all clear that it's a true statement. I think that it is true, but, you could certainly disagree. So one way to disagree, someone brought up this question. There was this paper they quoted by Susskind and Doher and Kleben, and they said, Susskind et al. Point out correctly, I should say et al. And Susskind, you always remember the most famous person on the paper, but they point out that it's not necessarily true that the dimensionality of Hilbert space is e to the entropy of it. And they say there's this sort of mysterious statement in the paper where that's only true if the temperature is infinite. The temperature is never infinite, so why are you thinking this, right? So what they have in mind is imagine a energy going vertically, and I just say how many states there are in the theory, right? Let me just list the number of states of some theory as a function of energy. And so there's some states, and this is the only picture I'm going to draw. This is it, okay? A bunch of states. But what this means is, and it goes on infinitely, so there are an infinite number of states in the system. So this, a simple harmonic oscillator is an example, right? There are more and more, there's an infinite number of states in a simple harmonic oscillator, but they have more and more energy. So what they're pointing out is that if you have a system at finite energy, then sure, you can have, in principle, infinite energy states, but there's not that many of them, or there won't be that much support for them in the system. So the actual number density of these states might go something like this, right? If I plot it this way, if I plot it horizontally. So basically, at fixed total temperature or fixed average energy, the chances that I will be in one of these super duper high energy states is infinitesimally small, so I can just ignore them so they don't contribute to the entropy. The case in which the dimensionality of Hilbert space equals e to the entropy is when every state in the system is equally likely in the statistical mixture that you're looking at. And that would not be true if you have a thermal system with arbitrarily high energy. But I don't think this is actually what we have here. I don't think that we have a system where there are infinitely high energy states. We just don't have access to them. Here we have, if you tried to make an infinitely high energy state, you would make a black hole instead, okay? So this is why we don't agree, or this is why we haven't yet settled down on what to say about these systems. But anyway, I think that if quantum field theory is not the right framework in which to be doing quantum gravity, that's very important. That has a lot of implications. And this argument is a very simple one for it. There's a related thing that I want to say. People asked about the expansion of space and the number of degrees of freedom. DOF, degrees of freedom, okay? So people, and this is something that is very confusing, and I was very confused about it for a long time. And again, I'm advertising my own papers, but it's my video series. I can advertise whoever papers I want, and I want to advertise mine. So again, this is something where I was confused, and I struggled for a while, and eventually I came to an answer that I liked. If you think about the expansion of the universe, the expansion of space, so here's space expanding, and this is time, then here's what you wonder about. We typically treat if we're just doing quantum field theory, if we really were taking quantum field theory seriously, then you would say, okay, there are modes that, long wavelength modes, and they evolve to long wavelength modes. They get stretched as the universe expands. And you might be tempted to say something like, well, I'm going to do an effective field theory with a cutoff. Remember, we talked about this when we talked about the renormalization video, like all that stuff I did, that we did together, the hard work in that middle period of the Biggest Ideas video series about renormalization and effective theories. There was a reason why we did all that stuff. It does feedback. We said, look, you put a cutoff, and you don't pretend to know what physics is going on at length scales below that cutoff. You only do the infrared physics, and you come up with a consistent theory that talks about that. So we can do that, and we're tempted to do that. In a non-expanding universe, that makes perfect sense. Well, when the universe is expanding, which it is, by the way, it runs into a difficulty. And there's different ways of phrasing the difficulty. Here's one way of saying it. There are modes here at this later time that here were smaller than the cutoff. Right? If this is the cutoff, whether it's the Planck scale or whatever, if I go backward in time, and my modes that I'm keeping track of expand or contract along with the universe, then any mode, like a typical photon in the cosmic microwave background, has wavelengths of millimeters or centimeters or something like that, okay? Like that big. If I shrink it back down to the super duper early universe, eventually it's going to be below the Planck length, or anything, right? Any wavelength you pick. So how can I simultaneously say that my theory only talks about modes above a certain wavelength when the wavelengths are changing as the universe expands? What's going on? Are new degrees of freedom being created out of nothing? And if so, why are they in their vacuum state rather than some other state? How do they know what state to be in, right? Okay, so nobody knows the answer to this question. Nobody knows for sure. We don't have a consensus on what the right way to think about this is. I did write a paper with some friends, too many friends to, let me see if I remember all the friends. Ning Bao, Charles Tsao, and Liam McAllister. We wrote a paper called Quantum Circuit Cosmology. And again, it's not exactly the new favored paradigm in the world, but I think it presents an answer to this. And the answer is, if you think about space-time as being constructed from entanglement between quantum mechanical degrees of freedom, then the way to think about degrees of freedom as space-time expands is not that more degrees of freedom are coming into existence. It's just that more degrees of freedom are becoming entangled with each other. So basically, we have a map, or we have sort of a relationship between the usual story of space-time expanding, okay, and we say that you can think about that quantum mechanically as there's a big bucket of unentangled degrees of freedom. And I will draw them as little arrows to mean, qubits. And I don't draw any lines between them, meaning they're unentangled. And this is just like a separate thing. In fact, let me put it over here. Let me draw it over here. This is like a resource that we have to draw from as the universe expands. And then we have actual space-time here. Oops. What we call space, which is made out of degrees of freedom, again, little arrows, but they're entangled with each other. Okay, and the entanglement gives rise to what we think of as the metric, the distance between them, and so forth. And so when space is bigger, there are more degrees of freedom, and they're entangled with each other in certain ways. Okay, and what happens is that this bucket of degrees of freedom still exists, but new degrees of freedom became entangled. They moved from the bucket into the set of entangled degrees of freedom. So there are now fewer degrees of freedom in our unentangled bucket. Okay? So there's a total number of degrees of freedom in the theory, but only a tiny fraction of them start out creating space-time. The other degrees of freedom, because they're unentangled in this bucket, just aren't part of space-time. And there's this what you and I think of as the expansion of space is not more stuff coming into existence, but entangling more and more degrees of freedom from this bucket. No one knows if this makes any sense, if this is somehow reflecting the ultimate truth of the cosmos, but this is the kind of idea we're playing with to make sense of these very difficult, very fundamental questions. I mean, one of the reasons why I like this field is because this kind of picture, I mean, it really is this kind of, we have equations in the paper, but this is the idea. Like, we didn't, reach this at the end of a long calculation. The questions we're faced with here are sufficiently difficult and fundamental that we're really thinking about what the basic question is, not working out details of some rigorous calculation. Okay. And one final topic on Boltzmann Brains. And I struggle with this particular question, because I get it all the time. It's not really a question; it's a claim that is clearly, in my mind, not correct. Maybe it's not even a claim. Maybe it's a potential thing to consider. And the idea is, look, I have a big box of gas, protons, neutrons, electrons, whatever kind of gas you want. And when I say big, I mean really, really big. And I just let them randomly fluctuate around for a long time. And according to the Boltzmann Brains story, if they are truly random and they have enough energy and enough time, occasionally they will randomly form a brain or a person or something like that. Okay, I have a large number of atoms. I have a really long time to wait. Eventually that will happen. Okay, but you can calculate how long it will take, very, very roughly. And the answer is way, way, way longer than the age of the universe right now. So a lot of people say, look, sure, maybe that happens, but clearly it's not the most likely way for it to happen, right? It's way more easy to make a brain if you start with a low entropy universe and just let it expand and cool, because then you make stars and galaxies, and you have thermodynamics, and entropy increases, and you get natural selection and evolution and the origin of life, and you're going to get a brain. It's a very natural thing. So, sure, maybe if you wait a hugely long time, brains will randomly fluctuate into existence, but that's not the easiest or best way to make a brain, so why should I care? Okay, I'm trying my best to sort of reconstruct what the argument is. So, in other words, isn't it easier to get brains? And again, when I say brain, I don't necessarily mean literally just a brain floating out there in space. Whatever you want. Okay, it could be a person, it could be a whole planet and a whole ecosystem. Whatever finite system with finite entropy you want, you can. The argument that I gave says will fluctuate into existence an infinite number of times, and most of the time it will fluctuate into existence without the rest of the universe coming with it. Okay, so when I say brain, if you prefer to think of person or ecosystem, by all means, think of it. To make a brain via evolution, let's say, by evolution we mean Darwinian natural selection in an ecosphere like we have, versus randomly. And the short answer is no. It is really not. Okay, but let me explain why I think this is an easy mistake to make. You have to compare two different things you might want to calculate. And remember, we did a whole video last time on probability, randomness and probability. And one of the things we talked about very briefly were conditional probability. So you have different events going on in the universe, and a conditional probability says, if I fixate on one thing having happened, what is the probability something else happened along with it? That's a conditional probability. So the difference is, if you compare the probability of a brain appearing to the probability of let's say the past hypothesis. So let PH mean past hypothesis. And that means, of low entropy, low early entropy. So the past hypothesis is just the idea that the early universe started with very low entropy. And we think that's true in our universe. But the question is, why? Do we need it? Etc. So this probability says, okay, let's imagine that we conditionalize on the universe being thermodynamically sensible. It started with low entropy, expands, it cools, you make stars, planets, galaxies, stuff like that. And I claim that it's not that hard to make a brain in that situation. Now, honestly, we don't know, because we don't know how easy it is to make life or whatever. But at least as far as thermodynamics is concerned, in this scenario, you're not, as far as we know, relying on any really, really, really unlikely random fluctuations. Okay? It is natural for complex systems like you and me to evolve in this kind of situation, conditionalized on the past. So we say that this is not small, right? This is the argument. The argument here is the probability of a brain with no past hypothesis. So this is not the logical not operator equals very small, right? Now, this is not plus you wait eternally long, but at any one moment, okay, if you didn't have a low entropy past, probably you have no brains lying around. Okay, you only get them by saying, well, we wait an infinitely long time. So this argument is saying, look, if I have the past hypothesis, it's more likely to get a brain than if I don't have the past hypothesis. Isn't that all I need to know? But the point is, that's not the thing you care about in this particular issue, in this particular argument. What you should care about, by the way I'm setting it up, it's obvious what I'm going to say here, is the probability of the past hypothesis being true given that you know you're a brain, not a bane, not a little Scottish baby. We know we exist, right? We know we're observers, we can think, we can look at the universe, we're alive, okay? Conditionalized on that knowledge, does it follow that the early universe probably started with low entropy? No, it really does not. Very small. That's the point of the Boltzmann brain argument, is that if all you know is that there's a brain, you cannot, by any stretch, conclude that there must have been a low entropy past. And the way to see that, it's not that hard, really. So like we have, real world, okay? The real world, again, here's space, here's the Earth, here you are on the Earth, okay? And so let's imagine that we want to get the whole Earth, okay? But so we have the Earth, but we also have the entire rest of the universe, right? So let me draw a little dashed line around the Earth. So we have, other stars, we have galaxies, black holes, etc. We have a huge thing, right? Trillion other galaxies in the universe. All of them, by the way, very, very low entropy. Very, very low entropy compared to what they would be if they were black holes. Very, very far from equilibrium, right? And you want to compare that to the fluctuated world, where you have the Earth. Let's say you fluctuate into the whole Earth, but outside it's just thermal equilibrium. So think back to the first couple of ideas videos that we did. Laplace, right? Conservation of information. You don't need historical knowledge in microscopic physics to figure out where you came from or where you're going. You need the current situation of the universe, whether it's the quantum state or the positions and velocities of everything. Okay? So what I do is I compare the likelihood of these two situations right now, at this moment. I don't need to compare their historical likelihood because it's the same. For every microstate that corresponds to these two situations, there's an equal number of past microstates that did because of conservation of information. Okay? So the fact that the real world has much lower entropy outside the part of the universe that we're conditionalizing on, namely the Earth and our ecosystem, versus the equilibrium plus fluctuation universe, means that this one is, in the ensemble of all possible states of the system, much more likely. So conditionalizing on the brain or conditionalizing on the Earth existing or conditionalizing under anything doesn't tell us anything about what happens outside what we're conditionalizing. Okay? You can tell me what you want, I can build the rest of the universe, and of all the ways I could build it, most of them have a much higher entropy than the real universe does, right? So that is enough. That argument is enough to guarantee that most of the ways that I could have to make the Earth and a person on it do not come from a very, very low entropy initial condition. In fact, there's you can sort of fine-grain that argument a little bit. You could put like a mini past hypothesis to give the people who live on the Earth here an arrow of time for a little while, okay? But most of the ways to get this macroscopic condition, Earth and you right now, have higher entropy in the past, right? That was Loschmidt's reversibility objection. It's still true in the absence of assuming a past hypothesis. Most configurations that evolve into this go from higher entropy and go down. Now, that doesn't mean we came from there. That means that Loschmidt's assumptions were wrong, that we should not treat all of the trajectories into and out of our current macrostate as equally probable. What it means is we should, in addition, assume the past hypothesis. That's why what we care about is figuring out why the early universe started with low entropy, and why saying that, well, we're here, therefore it must have been true, isn't sufficient. We still need some extra bit of cosmological information. Don't know what that is, but we're working on it. That's why, it's cutting edge science. That's why it's a lot of fun. Maybe, if I make follow-up videos 10 years from now, we'll have all of this worked out. Won't that be nice?